Here is a new article by a number of IPCC participants. These are people who participated in the reporting modeling centers and so on. And post facto to the AR6 coming out in 21 and 22, delayed by the COVID pandemic impacts, they have realized that the way the IPCC set up the working groups, first one, working group 1 focusing on physical scientific basis for climate change science, second one focusing on vulnerability, adaptation and impacts, and the third one focusing on mitigation, they find that there is a kind of a blind spot when it comes to what all these things together mean for water as a whole. As we know, potentially the entire globe is already quite stressed about water, not only in poor countries and tropics, global south, but also in the global north, if you look at what's happening in the US West, for example. And the way physical science bases and so on are working are very much focused on greenhouse gases, global warming, temperature focused, adaptation, etc. Also are considering things like extremes, which don't necessarily worry about long-term drying issues, for example, and mitigation, sometimes even including geoengineering, rely on using large parts of land for reforestation and various other geoengineering approaches, and even something like solar radiation management and what impacts they will have on land use and water demand and water stress and drying and so on. So they make a few good points that I'm going to record here as a brief introduction to the paper. You should obviously go read the paper if you want more details. We have already discussed several times that the models used in the IPCC scenarios and generally the climate models have fairly good skill in doing temperatures, either in prediction mode or projection mode. Even though at local scale there is still an issue, they can do reasonably large scale predictions and projections very well, but when it comes to precipitation, it's a big issue because of various factors, modeling issues and understanding issues, representation issues that we have talked about. And when you translate it to soil moisture and agricultural drought and so on, that gets even more complicated because of land use change, how we represent it, the data to constrain these, the processes and so on and so forth. And of course then there is the issue of the uncertainties that are dominated by model uncertainties in the first few decades after the period we are in now, let's say 2022 to 2040, 50, maybe model uncertainties dominate. Beyond that, the scenario uncertainties dominate. Keeping all these things in mind, what they do is start by looking at the historical observations and how models do during the historical period. So they define prior and posterior in a Bayesian sense to look at how observations can constrain the future projections of surface air temperature, land surface relative humidity, global land precipitation and precipitation over Amazonia as an example. And you can see that by the time you reach 2100, the corrected constrained projections are reduced by 33% for temperature, but only about 12% for land surface relative humidity, and 20% for global land precipitation, and 6% for Amazonian precipitation. So there are many details that you should read up, but essentially this means that model projections have uncertainties that can be significant. 33% is not a small number. There are several issues of climate sensitivity, and models are not doing the Pacific cold tongue very well. There are double IPCC problems, and whether the response in the Pacific will be El Nino-like or La Nina-like, and what that will mean for ocean heat uptake and global warming rates and so on, etc. I mean, there are many issues. Nonetheless, this gives you a sense that if we then go on to worrying about hydrological changes historically and with warming, then we will see again what kind of ranges we face. So hydrological changes over tropical land, annual means and interannual variability. So this is the synthesis of projected hydrological changes over tropical land areas relative to the base period of 1850 to 1900. So percentage change in 15 models for one scenario, SSP5 8.5. If you don't know what this is, you can go look up my other podcast, but essentially this is the business as usual scenario, which will give us the worst case warming as it stands. And looking at the relative changes, precipitable water mean is expected to increase with a range shown 70 to 83% range from observations shown here. And if you look at annual mean precipitation here, the increase is not that much, but and it's the range here 17 to 83% shown here, and this is the warming level. So with warming with respect to the 1850-1900 base, as warming gets stronger up to 5 degrees, the annual mean precipitation increases a bit in terms of percentages for this scenario, but the interannual variability increases a lot. This means that increased variance, even if the mean precipitation is almost the same, if the rain comes in with high variance, very dry periods, very wet periods, then that's going to have all sorts of impacts on water resources, agriculture, floods, droughts, etc. Right? So then you translate into runoff. So you can see the annual mean increases here with a large range when it comes to the 66th percentile range. And if you look at the interannual variability of runoff, again, that corresponds to the interannual variability of precipitation. Okay? Significantly high in terms of the range, the standard deviation. And if you look at how this translates to changes in likelihood of extreme agricultural or soil moisture drought years for 1 year long droughts, they don't consider multi-year long droughts. So start with the strongest warming at 4 degrees C, 2 degrees C, 1.5. Remember, this is our dream target, this is our next best hope, and then this is where we have not done well at all. So you can see there are regions where the changes in likelihood of an extreme single year agricultural drought can go up as high as 100%, and of course there are the normal expected regions like Sahara. There are regions in these are decreased likelihoods and these are increased likelihoods. So there are large areas with increased likelihoods, Western US, large parts of Europe, Mediterranean climate regions, large parts of China, all the way into mid-latitudes and high latitudes here, into Canada, and of course bad news for Amazonia in all these scenarios. 4 degrees C is the worst here, with likelihood of 250% increase in extreme agricultural droughts. You can look up the definition. The extreme agricultural drought is defined as the grid point 10th percentile of anomalies in total soil moisture, and that's what is going to give you a lot of stress in terms of water resources, agriculture, and so on. So the global south here is a rich target for this. India shows up here as basically having decreased likelihood, but this may be misleading because the Indian monsoon, which has shown a decreasing trend for the last 6 to 7 decades, is not done well in the models. There are debates about whether that's related to aerosol and solar dimming and land not warming as fast as it should, and so on. But nonetheless, there are also dynamic inconsistencies in models. So precipitation is always a big problem. When you go to soil moisture, that's even a bigger problem. But if you look at probability distributions of annual soil moisture anomalies in the South American monsoon zone, Mediterranean zone, and western southern Africa, the median value for the period of 1995 to 2014 is shown here, and the extreme of that period is shown here, to see relatively how the future shifts in these regions for various levels of warming. So you can see that for the South American monsoon zone, obviously with higher and higher warming, you are shifting towards a long tail of very extreme soil moisture anomalies, annual soil moisture anomalies. This is also the case, and you can see that the tail is quite thick here over the Mediterranean, which corresponds to the 4-degree warming and the extreme increases in the agricultural drought years as well. West-South Africa here, again, very bad for 4 degrees, bad enough already. This scale is close to 50 to 100%, and this is in the range of over 50% even for 1.5 degrees C. So this is something to keep in mind. The best goal we are aiming for, 1.5 degrees C as a global mean, will still produce lots of bad news all over. So this focus on temperature is going to be basically bad news for precipitation. So even if you are here, you have increased interannual variability and surface relative humidity and precipitation impacts that are not very well considered in climate change adaptation, mitigation, and in policies. That's the main point of this paper. So closing the IPCC loop, IPCC assessment is shared among 3 working groups. Working group 1 aims at assessing the physical scientific basis, as we said. Working group 2 assesses vulnerability of socioeconomic and natural systems to climate change, negative and positive consequences of climate change and options for adapting to it. And WG3 focuses on climate change mitigation, assessing methods for reducing greenhouse gas emissions and removing greenhouse gas emissions from the atmosphere. There are also countries like India arguing during the COP's Conference of Parties 27 that just concluded in Egypt that this desperate focus on mitigation as carbon reduction, and arguing that agricultural sector has to reduce emissions, just ignores the dependence of countries like India on agriculture. And then there is the argument about rice paddies, methane, it goes on and on. But all these are completely driven by temperature goals and greenhouse gas goals, and not paying attention to hunger, equality, equity, justice, and water, for example. Okay, cross-working group issues in the AR6: afforestation, reforestation with inappropriate siting and unsuitable species can exacerbate local water shortages. So they are not very careful in considering these. Undesirable consequences of remediation options on like solar radiation management can have serious impacts on the global water cycle. Less efficient global land carbon sink due to soil moisture limitations and associated drought conditions, which is what we looked at here. Carbon water trade-offs arising from the use of land-based mitigation options. Bold technological promises are being assumed, like bioenergy, for aiming towards global warming targets, net zeros, decarbonization, reducing emission, and so on, but they don't take very good care of water issues associated with them, and the limitations and maybe the lack of resilience of these afforestation, etc., with warming. Amounts of freshwater resources needed for an extensive deployment of bioenergy with carbon capture and storage, BECCS, and afforestation and reforestation. So this also needs very careful analysis to see whether at all this is feasible at large scale, and whether it will in fact be an effective mitigation strategy, and whether land use is going to more than compensate in ways that we don't understand. Adequate water availability for a massive expansion of hydropower capacity, which is considered renewable energy, but also for the cooling of nuclear power plants. So water is going to be needed there as well. To sum up, there are multiple ways to reduce our emissions of greenhouse gases with potential social and environmental co-benefits, for instance on air quality. Yet, and beyond financial issues, there are possible physical limits to mitigation scenarios. While finite fossil energy reserves may invalidate the highest emission scenario assessed in the Assessment Report 6, the low emission scenarios compatible with the Paris Agreement not only rely on sustainability of hydroelectric power generation, but also on the strengthening of natural terrestrial carbon sinks to absorb our residual greenhouse gas emissions. Are they really synergistic? Are they compatible with each other, or are they going to negate each other? We all have to worry about that. By so doing, the socio-economic pathways may not fully consider the hydrological consequences of the related emission pathways and the ongoing impacts already observed in the energy, agriculture, and forest sectors. This shows the urgent need for considering not only the feasibility of the different mitigation strategies in terms of the required technology or resources, but also, and probably more importantly, in terms of their social and environmental impacts, particularly in water-related aspects. It requires a more inter- and transdisciplinary view of mitigation. So mitigation simply focused on emission reduction, decarbonization, net zero is going to miss a lot of these things in setting the policies and making the choices. And this is a good cautionary note, so I wanted to include it here at this point under new findings in climate change. As you know now, the list is kind of very diverse, but everything that I find is important for climate change from every angle, from the 360 viewpoint I'm including here, so it's hopefully useful. Okay.